So the first question is, you have a diffraction gradient of 300,000 lines per meter. So what is the distance between each line? So I think you figured that out last time, didn't you? It's 1 over 300,000. So what did you get for that? 3.33. So that's 3.33 micrometers, yeah? Okay, very good. Next one. What is the angle for the second red light? So the formula is n, well, I'll write it down. N lambda equals d sine theta. Okay, here we know the n, it's 2. And do we know the lambda? We do. It's 633 times 10 to the minus 9. Do we know the d? We do. It's 3.33 times 10 to the minus 6. And we're looking for the theta here. So theta will be sine inverse 2 times 633 times 10 to the minus 9 over 3.33 times 10 to the minus 6. So 22.3. Excellent. Okay. C. Can I scroll? Yeah, no problem, no problem.
Okay.
Are you sure?
Yeah.
What is the highest order? So, n lambda equals d sine theta. You could change that into n lambda over d equals sine theta. But sine theta always must be less than 1. So it means then that n lambda over d must be less than 1, which means that n must be less than d over lambda. And we need to figure out what the biggest that could be. D over lambda is 3.33 times 10 to the minus 6 over 633 times 10 to the minus 9. So what does this fraction work out as? 5.3. So the biggest order is what then? Is 5. We can have at most order 5. Oh dear. Okay. Continue on deck, or do you need a minute?
Yeah.
Is that okay?
Yeah.
Okay. So now, D. The red light is replaced by blue light, and it's found that the diffraction angle for some order of the red light coincides exactly with the diffraction angle for the blue light in the next order spectrum. Determine the order of the spectrum for the blue light. So it's a bit hard, but I'll try and draw this. So here's your screen. And if you look at the screen, you'll get a red dot here, for example, and then 1, 2, let's just do 3 here. 1, 2, 3. So this order is 0, this is 1, this is 2, this is 3, this is -1, -2, -3, as an example, okay? And then you take the red light away and you put the blue light on. Now I'll keep the red light on in my picture here. So for one of them, let me try and draw this like here, 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 there, 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 for example. So you notice that the blue, except for the middle, of course, the blue and the red don't match up, except here, where they do match up. Now, what order of blue is this? Well, it starts at 0. This is 1, this is 2, and this is 3. So the blue order is 3 here. And what's the red order? 2. And then when it goes to the next one, they're not matched up again. So what the question is saying is, there's some order so that if the red is order x, in this example it's 2, then the blue will be order x plus 1. The blue has an order higher than the red. Some place where they will meet, and the only difference is the blue is an order higher than the red. Okay, now that's kind of tricky. So, if you were to use the formula, here's it for the red, and here it is for the blue. Now we don't know. In my example I said 2 and 3, but you know, who knows what it is. It could be 3 and 4, 1 and 2, something like this. So, n lambda equals d sine theta. So for the red light that is x, and that's the wavelength for the red light, which is 633 nanometers. That's equal to d sine theta. And we know the d, but we don't know the angle it makes, because we don't know what order it is. If you look at the blue, you get x plus 1 times, what is it for blue? 506.4 times 10 to the minus 9. And that's also equal to d sine theta. And you know the d, but you don't know the sine theta. Now here's the trick. Although you don't know the sine theta, you know that these should be the same. Because if the red and the blue are at the same point, then it means you have the same angle here. So this is the same as this, which means you can say x times 633 times 10 to the minus 9 should equal x plus 1 times 506.4 times 10 to the minus 9. Well, that's nice because that cancels with that. 633x equals 506.4x plus 506.4. So, what is 633 minus 506, please? 127 point. 126.6. That's equal to 506.4. So the x will be 506.4 divided by 126.6. 4. So the answer is the red at 4 will be in the same place as the blue at 5. So the 4th dot for the red will be where the 5th dot for the blue is. They'll be in the same point on the screen. Yeah. Yeah, you'll need to write that down. I don't think any of you's got that, right?
Do you have to try the line?
No. I was just trying to explain what was going on here. Need me to zoom out, is it, or you can see okay? oh, sorry, that's just me saying the red at 4 equals the blue at 5. Yeah? Continue? So the next part is okay. The question is, what is the angle for the second blue? So that's n lambda.
This is E, right?
Yeah, yeah. Equals d sine theta. And we want the theta here. So theta is sine inverse 2 times 506.4 times 10 to the minus 9 over 3.33 times 10 to the minus 6. And that's the answer for that. Say again, Sleepy Seabeth? 17.7. Why are you sleepy today? You go to bed late? I didn't go to bed till 1:30. Oh, I regret it. I was watching this TV show I found, I don't know if you've heard of it, Colony. You know this one? No. It's interesting because the idea is aliens came from space and they've trapped humans into colonies. So it's kind of like a, do you know the word dystopia? Yeah, dystopian future. So it's kind of like a gritty sci-fi show. It's interesting. It's interesting. I like that kind of stuff. And also I'm watching the new Star Trek as well.
Star Trek?
The new one, yeah. You don't watch that, right? No. You watch the old ones? No. Never. Not even one episode. Oh, that's so sad. You're missing out.
That was a movie.
You watched the movie at least?
I thought it was a movie.
Oh wow, okay. It was a TV show for like 30 years, you know. It started in the 60s. You should really watch an episode sometimes. You ever watched it, Andek?
No.
No. This is shocking from engineers.
I'm more of a Star Wars fan, so.
Star Wars, oh, no. Don't like Star Wars. Do you watch Star Wars? Okay, okay. So you're not into that type of sci-fi then. Right, the next one here. Oh, I tried that chicken burger in the mosque yesterday. It was pretty nice. But I didn't like the chips. The chips were a bit too soft. I like my chips crispy, you know. But the burger was nice. It's nice. Okay. The fringes were red in part A and then blue in part D. If the blue was replaced with white light, what colour would the fringes be? Okay. So if you look here, let's have a look at an example for the red light. At the very beginning we said for the second red one the angle is 22.3. So let me just draw it here. That's 22.3. Now the blue is a smaller angle, isn't it? 17.7. So for the second blue light, it'll be like here. So what will happen I don't know, you can kind of see the idea. You'll get a little rainbow of colours. If you put white light here, where you have red, orange, yellow, green, blue, you'll get all the colours here, but they won't match up. It'll go red, orange, yellow, green, blue, indigo, violet. You'll get a little rainbow here. So if you look at the screen, you'll get a dark spot in the middle, and then you'll get little rainbows here. So like for example, for the second one, you'll have red, then you'll have orange, then you have yellow, then you have green, then you have blue, and so on. So you get a little rainbow of colours. And you kind of know this because you see this happen when you have a prism and you put in white light. You get a little rainbow. And the reason for that is because there's a different angle for each colour. So that's how it splits it into the little rainbow of colours then. Okay? So the answer is you'll get a rainbow of colours. Okay. G, what is the fringe space then? So you have a formula for that. Oh my goodness, what is it? What is the formula? D over D. Lambda D over D. Did I use S or X for this formula? I used S. So for the red light, red light is 633 times 10 to the minus 9. And I say in the question that it's 1 meter away from the screen. Okay, so maybe Andek, you could type that in this time. Where is Matt and Kim? I know George is probably still out of the country. Matt and Kim? Oh, Kim lives on campus.
1.9 to 10 to the power of the t minus the t.
Oh no, that seems too small. Maybe I wrote some. Oh, did I write something wrong? Lambda. That's the lambda, isn't it? 633 for red times 10 to the minus 9.
So das ist eine Mathematik des Stroms.
0.190.
That sounds a bit better. 0.190 meters then. So that means these distances here are about 19 centimeters. The last part, H, my goodness, okay, this is a big one. Yeah? The last part is, how big does the screen need to be? So, what is the, do you remember what's, oh nice, nice. I had some for breakfast, so good. This is your breakfast now, is it? Yeah, okay. How many dots do we have? What's the biggest order? 5. So if you go 5 to the right and 5 to the left, then in total that's 10s, okay? But the S is different depending on the colour. So which would have the slightly bigger S? Which colour? Which is the one furthest out? It's the red, isn't it? Which is good because this was the fringe separation for the red anyways. My question is, how big does the screen need to be? It needs to be at least 10s for red, at least, which equals 1.9 meters. But you don't really want to use 1.9 because if you use 1.9 then it means the last one will be right on the edge and the red is here. That's not really accurate, is it? So I would recommend you should use 2 meters to be safe. So it's not too much bigger, it's just a little bit extra space so you can kind of clearly see the last one. So I think 2 meters would be a good length for the screen here.
So
Yeah.
what is 1.9 meter?
Oh, 10 multiplied by this. 10s. Because you have 10 fringes. You eat breakfast on deck?
No. Except for these lozenges, that's it.
That doesn't count. That so doesn't count. I had breakfast and I'm thinking about what would be good for lunch now. Chow, did you have breakfast?
No.
None of you had breakfast. You're having breakfast. This is terrible. Terribly sad. What's the reason? Just not enough time? Too tired?
I woke up late
No, that's fair enough.
and had to rush to the bus. So no
Fair enough.
breakfast.
For you, what's your reason? Just not feeling like food when you wake up, is it? Some people are like that. I'm not. Alright, have you got that? Can we scroll down? Chow, how come you don't have breakfast? No, why no breakfast? Ah, no, okay. Number two, I don't know. Well, you know what a CD is, don't you? Even if you don't use one, you still know what it is. This is how CDs work. I'll draw the picture here. I'll draw it upside down. So, I don't know why that one's upside down. You have here a laser. And what it does is it sends out two waves, okay? So here's one wave. Oh, sorry. It hits this and then bounces off. And then you have another, oh goodness. And you have another wave which is exactly the same. It's in phase, has the same wavelength. So we say it's coherent. So we have another wave here. It's exactly the same. Oh goodness. You get the idea, okay? Sorry, stupid looking wave. So what they do then, I can't quite remember it, but they do something where they have the two waves combine. Now if they're matched up, what type of interference is it here? Constructive or destructive? Constructive. So what'll happen is here you'll get a big wave. So it'll be twice as big. But what's interesting is here, when you have one wave here, and then the other wave doesn't hit it but continues on. So the wave that comes off here, and the one that comes off, oh, flip it. No, that's okay, sorry. These are exactly out of phase, meaning when they combine together, it will be what? What will happen? Cancel. So it'll be destructive. So as this laser moves along the CD tray, the CD surface I mean, when it is split between this and this, you'll get destructive. So you'll get no signal. And then here, you'll get a signal. And then here between these two, you get a signal. And then here, maybe you'll get here's no signal, signal, no signal, no signal, signal. You know what I mean? Like, the surface can represent signal, no signal, which represents 0 and 1. So this is how you can store the information on the CD. This is how CDs work. They send a laser down to the surface, a little red laser, and it switches between constructive and destructive. Okay? So the question now is, how big does this little surface need to be? Because you need this to be exactly out of phase. So the path difference here needs to be, now think about it, if you have one wave, how much do I need to move the other wave so that they completely cancel? So let's just draw it here. There's a quarter of a wavelength, half a wavelength, 3/4 and a full wavelength. So if I move it a quarter of a wavelength, will that cancel it? No. I would need to move it half a wavelength, yeah. Yeah, if I move it half a wavelength, then it'll cancel. So it means here the path difference is half a wavelength. And that path difference is caused by this distance. So it means this distance here should be half a wavelength. Do we know the wavelength? No, but we have a formula. It's we know the frequency. So the wavelength is c over frequency. So that would be 3 times 10 to the 8. And I tell you the frequency in the question, it's 7.5. So that would be 15 times 10 to the 17. So what do you get there for that one?
Two times 10 to the power
2 times 10 to
minus 10.
the minus 10, which is 20 nanometers, which is quite small. But it should be small, shouldn't it? Because when you put your hand on the CD, it feels smooth. Do you feel the little bumps? No. So it's supposed to be small. How do they make the little bumps on the CD? Do you know how? I think if you think about the vocabulary, what verb do you use when you make a CD? Or what would you say? You just say make a CD?
Yeah.
No, there's a verb. Have you ever made a CD before?
Made it.
Yeah, in the computer. Like put files on it to give to someone. Oh, yeah.
I've seen
What's the word for this? Oh, I'm shocked. You say burn a CD. Burn a CD. No? Yeah, you actually say copy but burn. Because what actually happens is in your computer, a laser is sent down to the CD and burns a hole into it. That's how it. That's how you can make the little holes. An actual laser burns the hole into the CD. So you realise this means that there's only so many times you can do this because then you'll burn everything away. So they have 2 types of CDs. One CD, they just put 1 layer on it and you can burn it once. And then the more expensive CDs, they put something like 1,000 layers on it and you can burn up to 1,000 times. You burn a layer off. You can actually, well, no, sure, you don't even use CDs anymore, so it doesn't matter. Yeah. USB keys only, is it? Yeah. Okay, so the last one there is 20 nanometers. Okay. So you see, these are a little bit tough, but the good news is there's just one lesson left which we'll do today, and then that's the waves already finished.